Okay, good morning to all of you. So we have in the new chapter we have started with the random processes, and in the last lecture we saw that how what is a random process and how what is the difference between a random variable and a random process. Then we also saw that what is a stationary random process where the PDF does not change with time. So it becomes a non-stationary, it becomes a stationary random process, right? So if we want to prove that a random process is a non-stationary process, only thing we need to prove is that the mean does not depend on, is not a function of time. The expected value is not a function of time. Then we also saw what is a strictly stationary process, then wide sense stationary process. And in my presentation, if you will see that there are some rules written. So whenever you are given a signal as a random process or any random process, if you are given, and if you are asked that prove that it is a wide sense stationary random process, then you have to actually prove those 2-3 conditions. One of the condition may be the mean is constant. The other can be the autocorrelation function. What is an autocorrelation function? Autocorrelation function is basically if let's say xt is the random process, then what is the dependency of the random process at xt and xt plus tau. So within the same random process, we want to know the dependency. All right. So that can be seen by the autocorrelation function. Then I also talked about what is cross correlation function. Whenever you are given two random processes like xt and yt, so what is the dependency on each other? For xt it is time t1, and for yt it is time t2. So we will find out the autocorrelation function, and if we can prove that the autocorrelation function is actually depends actually on t1 minus t2, the difference between the two times rather than the individual times t1 and t2, then we can say that it's a wide sense stationary random process. I have given examples also, and based on this theory, the tube sheet number 7 is actually prepared. So if you will try to solve the tube sheet number 7, you will be clear with all these terms and how to prove these random processes, either strictly stationary or non-stationary or wide sense stationary. All right. So let us now talk. I started with the Poisson distribution also. Let us look at the Poisson distribution once again. We will talk about the Poisson process, Poisson points, Poisson sum formula we will try, and we will also look today about the Markov chains. Very important concept in many fields like communication engineering or artificial intelligence, computer science. So Markov chains is a very important aspect of certain fields. Now, first, before we come to that, let us talk about what is the Poisson distribution. Let's just review it once again within 2-3 minutes, because we have already done it. Suppose that we can expect some independent event to occur lambda times over a specified time interval, right? The probability of exactly, so this is the average that we are expecting, but x is actually whatever is occurring. So if lambda is on an average, lambda events occur, some independent events to occur lambda times over a specified interval. So this is based on average, whereas x is the number of occurrences actually occurring, right? So the probability x is equal to x, right, or less than equal to x, we will see in the question. This is defined by x colon lambda, and this is given by lambda to the power x e to the power minus lambda divided by x factorial. This is the Poisson distribution. Suppose now, as an example, I started with this. That suppose a fast food restaurant expects 2 customers every 3 minutes. So it is expecting 2 customers every 3 minutes. on average. So what is the probability? So we have to find out the probability. That means we have to find out the probability of X. Now, what is X here? That 4 or fewer. So what is our X? X is less than equal to 4, either 4 or less than that. So that is our X for which we want to find out the probability. And what is lambda? Lambda is in 9-minute period we have to say, but given is 2 customers in every 3 minutes. So in 9 minutes you can expect 6 customers. 6 customers on average we can expect in 9-minute period. So we have lambda equal to 6, but what we have to find out, actually whether 6 customers come or not, that is not a necessary, that depends on the customers. The owner cannot bring the customers, but the owner is expecting 6 customers in every 9 minutes, right? So we have to find the probability that 4 or fewer patrons will turn up in 9-minute period. So how to find out that? 4 or less is there. So it can be 0, it can be 1, 2, 3, and 4. Exactly 0, 1, 2, 3. So all these probabilities we'll have to add. So that will give us the probability of customers less than equal to 4. This will be given by lambda to the power X. In the first term, X is 0, lambda is 6. So we can find out the answer. If you substitute the values, you will be able to see that the probability 4 or less customers comes out to be 28.5%. That means 28.5% chances are there that 4 or less customers will turn up in that restaurant with the given data. So fx is equal to lambda to the power x e to the power minus lambda divided by x factorial. X is equal to, the condition is that x is equal to 0, 1, 2, 3. These are positive integers, right? This is known as the probability mass function of the Poisson distribution. Correct? Now, what is a Poisson process? We talked about the random process. Let's now look at what is a Poisson. So it's a type of counting. I mean, which type of examples you deem to be fit for applying this formula, right? Where you will be applying this formula, that means you will categorize, you will characterize those processes as Poisson processes. So let's look at the characterization of the Poisson process. So it is a type of counting process in which random variable counts something over a specified interval, time interval. So this is the pretext on which you can apply this formula, and then you can say that this is a Poisson distribution. The Poisson distribution fits well to this kind of problem. Type of counting process in which random variable counts something over a specified time interval. It can be the number of calls received per hour by an office. Suppose somebody is counting the number of calls received per hour, so that becomes a Poisson process. The number of customers in a particular hour in a restaurant, again it becomes a Poisson process. You're counting within a specified interval of time. The number of earthquakes in Delhi per decade, this is again a Poisson distribution, right? So the time period is very large, but it's again a Poisson process, right? So now there is a very important, actually, before I come to the Poisson summation formula, let me talk about the Poisson points also. It is a random, so what is a Poisson point process? The same thing, actually, whether you want to discuss Poisson points, whether you want to discuss Poisson point process, or a Poisson process, or a Poisson distribution. Everything revolves around that distribution which I just talked about, lambda to the power x e to the power minus lambda divided by x factorial. But these things also need to be understood, because if you are trying to model a certain process, then you have to partition the process properly so that you can have a full mathematical modeling of that process. So what are Poisson points? Poisson point process, first of all. It is a random mathematical object that consists of randomly located points on a mathematical space. So this is the mathematical space. So it is a mathematical, random mathematical object that consists of randomly located points, right? Now, Poisson point process is often called the Poisson process. Now, a visual depiction of Poisson point process, starting from 0, if you start from 0, let's say, in which the increments occur continuously and independently at rate lambda. So as in our example, I talked about that 2 customers you are expecting in 3-minute period, right? So lambda or in a 9-minute period, you put lambda equal to 6. But let's say if it is a 3-minute period, so lambda will be equal to 2. On average, as an expected value, saying that 2 customers will enter the restaurant in 3-minute period, right? So the first point is, let's say, the starting point. After 2 minutes, we reach to this point 1. That means 2 customers will enter. After 2 minutes, again, we'll reach to the point 2. That means after lambda. So this is a kind of object, mathematical model, the expected mathematical model for a Poisson point process. And these points after the specified interval, where we will sample how many customers have come. That means expectedly 2 customers will come after 3 minutes. This 0 represents the start of the time. This 1 represents after 3 minutes. The 2 represents again after 3 minutes. But this is all on an expected level. This is not actual, right? So a visual depiction of Poisson, and these 0, 1, 2, 3 are known as the Poisson points. And this process is known as Poisson point process. A visual depiction of Poisson point process starting from 0, in which increments occur continuously and independently at rate lambda. So lambda is at an expected level, on an average level. Now, if a collection of random points in Euclidean space, so if there are a collection of points in the Euclidean space, what is the Euclidean space? A point in 3D Euclidean space can be located by 3 coordinates. So a point in Euclidean space, normal Euclidean space, for example, if you want to represent a point using a planar surface, you require 2 coordinates. A 3D surface, you require 3 coordinates. So that is basically Euclidean space. One is x-axis, y-axis, z. So these points, because at the understanding point of view, if the problem is related to, let's say, a customer entering into a restaurant, if the problem is like that. But if I want to model that process, that example, in the form of a mathematical, geometrical solution, then I can put every point, right, in a 3-dimensional space. It can be more dimensional space also, but that will be Euclidean space. And those points will be called as the Poisson points, and the overall process will be called as the Poisson point process, right? So, okay. The number of points in a region of finite size is the rank. So this is how many points are there? Coming back to my example, after 3 minutes, you will have 2 customers at an expected rate. So this is my first point, second point, third, fourth, and so on. So these points are actually the collection of these points constitute a random variable. That's what is said here. That the number of points in a region of finite size is a random variable with Poisson distribution. The Poisson distribution is the probability distribution of a random variable n called a Poisson random variable, such that the probability that n equals a small n. In my earlier slide, I used x, right? Here it is small n. So I can say that probability n equal to small n is given by lambda raised to the power n e to the power minus lambda divided by n factorial. Meaning is the same. This is more at a more mathematical understanding point of view. If you want to, model a complex process, complex Poisson process, then you can model it like this. Now lambda is the the rate at which the events occur. Lambda determines the shape of the distribution. If a Poisson point process has lambda of the form lambda equal to nu a, where nu is Lebesgue measure, it is science. Nothing to worry about this point. Let's leave this point for the time being, because this is more of a mathematical concept about the stationary or the homogeneity. If the if lambda is of this form, nu a, where nu is a certain measure which assigns length, area, or volume to the Euclidean space, and a is a constant, then it will be called as a stationary or a homogeneous Poisson point process, right? So let's come back to the Poisson summation formula. This is also included in your syllabus. So we know that what is a Poisson process. We know that what is Poisson distribution. We know how to, as I have given you one example where you can solve questions, where you can model a process to be a Poisson process. Now there is very important relationship that we need to prove here, which is Poisson summation formula. Actually, if you can answer me this question, somebody is there in here. Are you reading or have you read Fourier transforms? Can somebody respond to this question? Hello? Let me see.
Exactly.
The question is that, have you read in your syllabus sometime, because it's a signals and systems topic, Fourier transform. Have you read it, or are you reading it, or have you not read it?
I haven't read it. Fourier transformation.
Fourier transform, have you read?
So we know about Fourier series, don't know about Fourier transformations.
Okay, so Fourier series, so that means only thing to prove this summation formula, I will give the expression, but don't worry about if you don't know what is a Fourier transform, because you will study Fourier transform in detail for 2-3 courses rather. One is signals and systems, then digital signal processing, then digital communication. So all these 3-4 courses you will study Fourier transform in detail. So nothing to worry about, but I will give you the expression just to prove this formula. But let me explain what is this Poisson summation formula is. Now this formula is like this. This is a function fn, right? Argument is n, so this is a function. Summation of this function from n varies from -infinity to +infinity. If you sum the function where the argument will vary from -infinity to +infinity, now what is this equal to? This is equal to the summation n going from -infinity to +infinity of what? Of the Fourier transform of this function. This is a very, very strange kind of result. The summation of a function from n going from -infinity to +infinity is actually equal to the summation of the Fourier transform of that function. Right. Sum from n minus infinity to +infinity of some function fn is equal to a sum from n minus infinity to +infinity of the Fourier transform of that function. So this is known as Poisson summation formula. Now, what is Fourier transform? There are various conventions to describe Fourier transform, but the Fourier transform of a function in general, this capital F is the Fourier transform of this function. And this is normally represented by f cap k, right? And what is the formula? The formula is integral from -infinity to +infinity of what? Of fx of this function e to the multiplied by e to the power -i 2 pi xk dx. So this is the Fourier transform formula. Fourier transform will actually give you the idea about the frequency components present in a signal or any random process. All right. But for the time being, what is the Fourier transform? So this is the Fourier transform, right? Now, starting from the right hand side, right? We will come back to the okay. We will start from the right hand side and we will reach to the left hand side to prove this formula. Now, what is this formula? Right hand side, this is summation n going from minus infinity to plus infinity and the Fourier transform. Here, while defining the Fourier transform, I use the index k, but since in my actual formula I'm using n, so instead of k, I will use n here, right? So if it on the right hand side, if it is the Fourier transform of the function, so I can definitely put it like this: sigma n going from minus infinity to plus infinity, integral minus infinity to infinity, fx e to the power minus 2 pi x n dx. Correct? Now there is a concept in mathematics where we can change the sum and integral, interchange the sum and integral, right? So interchanging the sum and integral will come outside, summation will go inside, n equal to minus infinity to plus infinity, e to the power minus 2 pi I n x dx. We can interchange this kind of, we can do the interchange. Now, again, this formula is the result of the signals and systems course. Please take this result as it is, because the proof of this, the important thing for you to remember at this point is this Poisson summation formula. Please don't worry about, though I am doing the proof, right? Please don't worry about how these results are coming. Now we know from signals and systems that summation e to the power I n x, this is given by 2 pi k going from minus infinity to plus infinity delta function of x minus 2 pi k. Here it is minus sign, but this expression is for our positive sign. This is a given result. I will use this result to substitute in this expression, right? So once I do this thing in the expression, because 2 pi is there in the result, so 2 pi will come outside. And if you see here, this is I pi I n x, but whereas here it is minus sign, so definitely you will get delta minus 2 pi x minus 2 pi k dx. So this has come from where? This has come from this expression only, using this result of signals and systems. Correct? Now from the property of delta functions, again, don't worry about it. See, I have to prove this result. Only 2-page proof is there, but I cannot go at present doing the signals and systems course. Though we will have to look putting this Poisson summation formula from next time. I will talk to head of the department that once the Fourier transform is not done and the results are not, why we are putting it here. We can put it somewhere else. But anyway, right now we will do this. No problem. Nothing to be worried about. Okay, I'm sorry. I'm really sorry. Yeah. So this comes out to be, now there is a property of the delta function. Delta functions are even functions, right? Even functions means across the y-axis, the functions are same. Right? Whatever is the function on the right side of the y-axis is the same as the function on the left-hand side. So that's an even function. So we can treat this negative sign as positive sign. And also this is of the form of some constant times of the argument. So this is 2 pi. Once we are taking the negative sign out, we are taking the positive sign, 2 pi x plus 2 pi k. So 2 pi is a constant, 2 pi into x plus k, right? So we can take 2 pi outside. That will become 1 over 2 pi here. And this 2 pi is outside already. So 2 pi will cancel with 1 over 2 pi. And what we are left with, integral minus infinity to plus infinity fx delta of x plus k. Using the results of signals and systems. Please mind it. So once this delta function is multiplied with this fx function, you will get it equal to fk, right? So that proves the result. Hence, it is proved. From where we started? We started from the Fourier transform of a function using some manipulations of interchanging the sum and integral and doing some signals and systems research. We can reach to the left hand side of this Poisson summation formula, where we can say that the summation of the Fourier transform of a function is actually equal to the summation of that function itself. That is Poisson summation formula. All right. Now, so this is all about the Poisson. This we have already done before the this first sessional exam. But let us now come to something more interesting, which is Markov chains. Very interesting concept, used in marketing, used in management, used in engineering, artificial intelligence, machine learning. So many things are there, right? So let us try to understand what are Markov chains. I will define the Markov chain more systematically, maybe in the next slides. But before that, I would like to take an example. The example says that, suppose a very interesting example actually this is. You will really find this example very interesting. Suppose that an apple juice company. Now that apple juice is, let's say we will call it as brand A. Now this apple juice company selling this brand A controls 20% of the apple juice market. So brand A actually controls 20% of the apple juice market. The company wants to do, now certainly if it is a 20% market share, every company would like to increase that share. And how they can increase that share? One of the way is to do an aggressive advertisement. The company wants to do an aggressive advertisement campaign, and for this purpose, they hire a research company to predict the effects of that advertisement. So they decided to go for the advertisement, but they also hired a research company that will actually look into the effects of that advertisement, that how much share is increasing or decreasing or what is happening in the market. Now, suppose they conclude, the research company, they conclude that after this advertisement, after 1 week, what they conclude? Someone using brand A, someone who was using brand A will stay with brand A. He will continue with brand A only with 90% probability, right? So someone not using brand A, earlier somebody who was not using brand A will switch to brand A with 70% probability. So the first statement tells me that people who are using brand A, there is a 90% chance, 90% probability that they will stick to brand A. But 10% chance is still there that they will shift from brand A to some other brand. But the second point tells me somebody who was not using brand A, but it can come to brand A with 70% probability due to the effect of this advertisement. So this is a 1 week analysis. People buy apple juice once a week, right? So we want to, see the market share after 1 week. What is the effect on the market share? Earlier it was 20%, but now what is the market share at present with this advertisement campaign? So I will use some notations. For brand A, I will use A as the notation, and somebody who is not using brand A, I will represent that as A prime. So let us make a diagram which will tell how the transitions are happening. This is known as the transition diagram. Now, what is this transition diagram? Just to represent the probabilities exactly in the form of a state diagram, right? And this is known as transition diagram. Now, this A is the state. That means somebody who is using brand A, and if the arrow comes here, it tells me that somebody who was using brand A, after the advertisement campaign, he will continue using the brand A. And that probability is given to be 90%. So that means 0.9, we can put it here. But there is a 0.1 chance that it will go to some other brand, A prime. So we can represent it like. But in the second line, it is given somebody which is not using brand A, so which is using some A prime, 70% chances that it will shift to A. So I can represent it like this: 0.7 probability is there that it will come to brand A. And 0.3 probability, of course, is there that it will continue using some other brand. So these are the statements, but this is the transition diagram. Explains the same thing. This is known as state diagram or transition diagram of the Markov chain. All right. Then we can represent these probabilities. This is the transition diagram. We can represent these probabilities in the form of a probability transition matrix also. Now, how to write the probability transition matrix? It is generally denoted by capital P. Along the horizontal or along the vertical side is the previous state, right, or the current state. Along the horizontal side is the next state. And how many states can be there? Either brand A or not brand A. What can be the next states? Either brand A or not brand A. So let us look at the matrix. So if somebody is using brand A, will continue to use brand A with 0.9 probability. Same thing. Somebody who is using brand A will shift to some other brand with 0.1 probability. Somebody who was not using brand A will start using brand A with 0.7 probability. And somebody who was not using brand A will continue with some other brand with 0.3 probability. Same thing explained in the statements, same thing explained in the transition diagram, same thing explained in the form of a probability transition matrix. This is a very standard form of representation of the transition probabilities. Along the vertical direction, it is the current state. Along the horizontal direction, we represent the next state. And there is one more matrix. What does the question say? 20% market share was controlled by brand A. This is the state of the brand or state of the juice company initially. And if we put it in the form, so this S0, the initial state distribution matrix. It says what? It says that how many people who are using brand A? 0.2 with 0.2 probability. And how many, what is the probability? What is the market share of some other brand? It is 0.8. This is known as the current, this is known as the initial state distribution matrix. Market share initially. And one more thing, one more way to represent these transition probabilities is the tree diagram. So let us look, starting from here, 0.2 is using brand A, 0.8 is using some other brand. After 1 week, 0.9 will use brand A. Out of this 0.2, 0.1 will shift to some other brand, which we can represent as A dash. 0.8, which represent the population which are not using brand A, but 0.7 will start using A, and 0.3 will continue using some other brand. This is known as tree diagram. This is known as probability transition matrix. This is known as state diagram or transition diagram. These are known as the statements. Same thing expressed in different ways. But all these things are very important that you must understand what is a tree diagram. This probability transition matrix is very important, right? And so what we want to find out, what is this is the initial state distribution matrix. We want to find out after this ad campaign, what is the state distribution matrix. So probability that someone use brand A after 1 week. After 1 week, we want to know what is the probability that how much percentage will start using the brand A. Now this we are using the multiplication rule from this tree diagram itself. So 0.2, we have to go for brand A, 0.2 multiplied by 0.9 plus 0.8 multiplied by 0.7. This corresponds to brand A. This will come out to be 0.74. So after the ad campaign, the market share, which was 20%, will expectedly can go to 74%. So this is the multiplication. This is using the multiplication principle, but we can use one more method, more systematic method. The S0, which is the initial state distribution matrix, it is 0.2, 0.8. We want to find out S1. How can we find out? Multiply S0 with the probability transition matrix. Multiply the initial state transition matrix, initial state distribution matrix with the probability transition matrix. 0.2, 0.8 multiplied with this transition matrix. You will get a new state, which is known as S1. First state matrix, which says that 0.74, 74% will start using brand A, 26% will continue with some brand A. Now, after 2 weeks, after the next iteration, what we will do? We will use the S1 to multiply with the probability transition, assuming that the probability transition matrix remains the same. We multiply the S1 with the same probability transition matrix, same results. We get S2, result after second week. It comes out to be 0.848, 0.1. 85% will start using brand A, though the increase is not that significant after 2 weeks. After 3 weeks also we can find out, and so on. After 3 weeks you find that this is 86%. So the increase is not significant from 85 to 86%. All right. So these are known as Markov chains. Markov chains. All right, let's what's the time? The time is 11:08. I can go with I will stop sharing this screen and we'll use some other screen. We'll use some other file. I will stop sharing this file because that will actually finish the topic. Let me just find out. क्लास चल रही है भाई, wait. Okay, this is the, let me just I will share the next page, which will actually explain. Yeah, this is it. So I hope you are able to see the all right, I have already done with the Poisson summation formula. So we can, let me just do the full view, full screen mode. Formula, right? So, but what I want to discuss here is the Poisson summation. No, I have to actually wait. Yes, I want to discuss this. Yeah, I want to formally represent what is a Markov chain and what is a Markov process. Now let X be a random process and is in state xt at time t. So in Markov chains, the random process state xt plus 1. What I mean to say is that if let's say the next state of a Markov chain is, I represent it with xt plus 1, and the previous state is xt, previous to that is xt minus 1 going to up to x0. So the next state is xt plus 1, then it is xt previously. What are the states of a random process or in a Markov chain? These states are x0, x1, x2, x3, xt minus 1, xt, and xt plus 1. Xt plus 1 is the next state. Xt is the current state. Xt minus 1 is the xt minus 1 up to x0. These are the past states, right? So in a Markov chain, this is the important result. Let me show you the result. In a Markov chain, the important result is that, just let me show you the result actually. Okay, from okay, yeah, this is the so probability that the random process will be in state xt plus 1 will only depend upon the previous state, not the next state, not the previous state, the current state. Let me explain you, right? The probability that the random process is in next state, which is represented by xt plus 1, right, will only depend upon the state or will only depend upon the current state xt equal to st. The point that I'm trying to mention here is that because it's a Markov chain will have a state initially, let's say S0, as we were talking in the example, S0, then S1, S2, S3, S4, S5, S6, let us say up to S10. So S10 I denoted by ST, let's say that's the current state. So S11 is the next state, right? In a Markov process or a Markov chain, the next state will depend only upon the previous state, not on the next state will depend on the current state. Current state is my xt. Xt plus 1 will only depend on xt, will not depend on xt minus 1, xt minus 2, xt minus 3, x0. That's the point. This is known as a Markov chain. This is a special property of the Markov chains, which is known as the Markov property. So let X be a random process and is in state xt. This is the current state at time t. In Markov chains, the random process state xt plus 1, this is the next state, will only depend on the current state. It does not depend upon xt minus 1 and other past state. If you take a random walk, none of the previous steps matter. Whatever are the steps at time t plus 1 will only depend on whatever the steps are there at time t, not on the previous steps. I will discuss in detail about the random walk model, okay, in the coming lectures, because that is also included in your syllabus. That is random walk model. So the important point that I want to mention here is that the next state will depend on the current state only, will not depend on the past states. In Markov chain, the future depends only on the present and not upon the past. That's the property of the Markov chain, which is known as the Markov property. A Markov chain is the process x0, x1. That's an example. I think to be. So that's what mathematically we can put as a Markov chain. That probability xt plus 1. This is the next state. The probability the random process is in state S. Next state is S. Will conditioned on previous state as current state st, previous state st minus 1 as 0 will only depend upon the current state. Probability xt plus 1 equal to S conditioned on xt equal to st, xt minus 1 equal to st minus 1, x0 is equal to s0 and so on will only, this is equal to the probability that the random process, the next state of the random process is S will only depend upon xt, that means the current state, will not depend upon the previous state. That's the meaning here. That's the mathematical meaning of the Markov process. Right? Let x0 be a sequence of discrete random variables is a Markov chain if it satisfies this property. That it depends on the next state depends on the current state. It does not depend on the previous states, the past state. That's the basic, that's the moot point of a Markov process. All right. This is the transition matrix that I was just trying to explain. This is another state diagram. Two things are there, two states are there. One is hot and cold. So I can plot a transition diagram. Along the vertical side will be the states, either hot or cold. And the horizontal direction will also be states, hot and cold, but horizontal direction will represent the next state. The vertical direction will represent the current state. So it will remain in hot with hot to hot, it will do with 0.2 probability. Hot to cold, it will go with 0.8 probability. Cold to cold, it will do with 0.4 probability. Cold to hot, it will go with 0.6 probability. So this is the another example of the probability transition matrix. This is a general form of the probability transition matrix that the horizontal direction is the next state, the vertical direction is the current state. So these are the probabilities which with which we need to fill this probability transition matrix. The rows represent the current state, that means X. Now, I'm trying to put it in the form of an English, like word kind of thing. It is now, the columns represent the next states, right? So the important thing is that the sum of the rows, the sum of the rows of P should sum to 1. Rows of this transition matrix should sum to 1. And it is not necessary that the columns of P should sum to 1. It is not, do not in general sum to 1. Right. So another example can be taken. The example is that consider the Markov chain with 3 states, 1, 2, 3. So 3 states are there, 1, 2, 3. Along the horizontal direction, there will be 3 states, 1, 2, 3. So this is the probability transition matrix given. Draw the state diagram. So state diagram we can draw. How we can draw? 3 states are there, 1, 2, and 3. This says that previous state is 1, next state is 1 with probability half. So previous state is 1, next state is 1 with probability half. Previous state is 1, but next state is 2 with 1/4 probability. Previous state is 1, next state is 2 with 1/4 probability. This is how we can draw the transition diagram. Now the given is that the probability x1 is 1, probability x, the random process is in state 1 is equal to 1 is equal to 2 with the probability 1/4. That the random process is in state 1 or state 2 with 1/4 probability. Find the probability x1 is equal to 3, x2 is equal to 3, x3 is equal to 1. These are x1, x2, these are the time intervals. That first time interval, it will be in state 3. Second time interval, it will be in state 2. Third time interval, it will be in state 1. But we are given with what? In time 1, probability, if the random process is in state 1 or state 2 is with 1/4 probability. So if this is the case, then total probability, this is the probability of the random process in state 1, state 2 is 1/4. So total probability, how many states are there? 3 states are there. Total probability is going to be 1. All right. Okay, the class is, we have to finish the class actually. The time is over. I will continue, I will do the example once again, no problem. Thank you.